Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about the alternative fuels. In the last class we have talked about the self ignition characteristics of the fuel. We have also discussed about the fuels for both SI and CI engines. So, if we discuss today briefly again what we had discussed in the last class is this self ignition characteristics. So, before going to discuss this part today again, let us first draw the schematic of two engines, that is SI and CI, that will this is top dead center and this is bottom dead center, and for this SI engine, the name itself suggests that spark plug will be there, and if we draw similarly the compression ignition engine, we have fuel nozzle. So, that is used to spray fuel into the combustion chamber. Fuel nozzle. So, for the SI engine, through the intake manifold we take charge, that is air plus fuel mixture. So, this is charge, but for the CI engine only fresh air is taken into the cylinder during intake stroke. So, this is only air. Now, we have discussed so many times that whether it is the charge, that is air fuel mixture, that is that air fuel mixture is there inside the combustion chamber, or if it is only air for the CI engine, that is what is we have discussed in the last a few classes. The air or air fuel mixture will be compressed during compression stroke. Now, for the SI engine, during compression stroke, that is compression heating, the temperature of the air fuel mixture will be increased. Similarly, temperature of the air also will increase during compression heating, and towards the end of the compression stroke we need to supply fuel through fuel nozzle. The temperature which is developed during compression heating of the air fuel mixture or air is very important. That temperature for the compression ignition engine, that is the principle of the compression ignition engine, should be higher than the self ignition temperature of the fuel itself. So, what is the self ignition temperature? That is the temperature at which fuel will auto ignite, self ignite. So, that is why the word self ignition is there. So, that means compression heating, that rise in temperature due to compression heating should be such that it should be higher than the temperature which is required to auto ignite or self ignite the fuel for the CI engine, and that is the principle of the compression ignition engine. Now, for the SI engines, that temperature is also having an important role. So, we have agreed undoubtedly that the self ignition temperature is very important for the CI engines, because this temperature should be known before a particular fuel is selected for the engine, right, for the of course for the CI engines, because the rise in temperature due to compression heating should be higher than the self ignition. Otherwise, what will happen, that the mixture will simply cool off, it will not take part in the combustion. On the other hand, so we are claiming that the self ignition temperature SIT, so self ignition temperature or SIT, this is very important for the CI engine, but it is also important for the SI engines. Why? Because you know that if we do not know about this particular property of the fuel, then what will happen? If the self ignition temperature of the fuel that is being used for the SI engine is very less, then we may not require even spark plug to ignite the fuel. So, what will happen, that we are using spark plug, that means we are not going to utilize the self ignition property of the fuel. So, the fuels which are normally used for the SI engines are having low self ignition temperature, and that is why this external agent is needed. Question is, if we do not know about this particular property of the fuel even for the SI engines, then it would be very fatal for the engine operation. Let us discuss briefly on that. So, if the temperature rise during compression heating is above the self ignition temperature of the fuel which is used for this particular SI engine, then one flame front will come from the spark plug, because spark plug is there. So, spark plug will ignite the fuel which is there closer to this region. So, the compressed mixture would be there, and the compressed mixture which is there in the vicinity of the spark plug will be ignited first due to the spark plug, and then the flame will propagate across the combustion chamber and the entire charge will be combusted. But if the self ignition temperature is very less, maybe the rise in temperature due to compression heating will allow the fuel which is there even at the furthest location of the from the spark plug will also ignite, and the resultant effect would be abrupt rise in pressure, and that too that is kind of very chaotic. So, abnormally pressure will be developed inside the combustion chamber, and the pressure pulses will cause the damage of engine and several parts of the engine, and this is very undesirable to the I mean this is not a desirable for the smooth operation of the engine, because the rise in pressure would be so high and it would be abnormal. So, it will create an audible noise alongside several other effects like damaging of several parts of the engine, and the entire phenomenon is known as knock. So, to prevent the knock of the SI engines, knowledge about the self ignition temperature is equally important, though it is highly important for the CI engines, because the principle of the CI engine is based on the kind of self ignition property of the fuel, but we have also understood that it is also or equally important for the SI engines, because to prevent an undesirable phenomenon which is known as knock. So, if we go to the next slide, we have discussed that. So, we have understood that the fuel property that describes about the self ignition characteristics of the fuel. In other words, the fuel property which describes how well a fuel will ignite or will not ignite is very important, right. So, let us briefly discuss about the graph that we had discussed in the last class, that is the time, this is temperature. So, we had seen if we consider a particular fuel and if we assume this is the self ignition temperature SIT. So, this is self ignition temperature of that fuel, and if we compress the fuel for the CI engine, of course, if we compress the air, or for the SI engine if it is the charge, that is air fuel mixture, and if we compressed the charge or air during compression heating, you can understand that with time temperature will increase. If the temperature of that particular temperature rise because of that compression is less than the self ignition temperature, then fuel will or the mixture will simply cool off and it will not take part in the combustion. On the other hand, if I use another case, if I represent another case where the self ignition temperature is above the the rise in temperature due to compression heating is greater than the self ignition temperature. So, this is the rise in temperature above the self ignition temperature. So, understand this is the rise in temperature above SIT, and then self ignition will start over here at that point, and we have discussed about the ignition delay. So, this is the ignition delay or ID, and then this is the rise in temperature due to combustion, right. So, self ignition starts here, it is because of this ignition delay eventually combustion, the entire combustion will start from here, and then we can see that abrupt rise in temperature. And this ignition delay that is having two different components, one is physical delay, another is chemical delay. These two delays together from the ignition delay, and what will happen, that if we can make sure that the rise in temperature of the mixture or of the air due to compression should be even larger than the self ignition temperature. So, if I consider another case, then we can see that the ignition delay period is reducing. So, this is the ignition delay 2, right, and this is ignition delay 1, right. So, basically two things are very important, one is self ignition temperature, another is ignition delay. So, this is the ignition delay and this is the self ignition temperature. right. So, these two are very important to know about any particular type of fuel before we use that fuel for the combustion of internal combustion IC engines. Now, the prediction of SIT or ID, that is self ignition temperature and ID for any given air fuel, for any given air fuel mixture is ambiguous, because it is not fixed. It depends on so many factors like pressure, temperature, swirl, turbulence, so many things. So, a perfect knowledge about the ignition delay is also very important for the compression ignition engine, because we are going to utilize this self ignition or auto ignition property. So, we had seen that the self ignition temperature together with the knowledge about ignition delay is very important, because these two things are very important for the efficient and smooth combustion in CI engines, compression ignition engines. So, as I told you that even for a given air fuel mixture, these two quantities are not fixed, rather ambiguous. It depends on so many factors I have already told you. So, what next we will be discussing today is the two important numbers. What we have understood till now, that the fuel property that describes how well a particular fuel will self ignite or will not ignite, right. So, let me write here is, so try to understand, if we talk about CI engine, compression ignition engine, compression ratio is fixed, we are increasing the temperature of air during compression heating, and then we are discharging or we are spraying fuel into the combustion chamber. At that prevailing condition, whether the combustion will be completed or combustion will be initiated, that depends on a property, right. So, basically which is that property, that means whether the fuel will ignite or will not ignite, because we are not having any external agent to ignite the fuel for the CI engines. So, the fuel property that describes how well a particular fuel will ignite or will not ignite is known as octane number. So, today we will be defining two different number, one is octane number or simply octane, or octane. What is this? So, this is the number which is used to describe the property of a fuel which indicates whether that fuel will self ignite or not, right. So, this is very important. So, the fuel property that describes how well a fuel will ignite or will not ignite, right, is the octane number, right. So, octane number is defined as the fuel property that describes how well a fuel will ignite or not or will not ignite. Now, question is, so if you would like to have this number for any fuel, any test fuel, maybe that fuel will be used for the SI engine or CI engine. So, to know this, the number, to know the numerical value of this number of any test fuel, what we need to do? We need to compare that fuel. What we need to compare? We need to compare the self ignition characteristics or self ignition property of the test fuel to that of the two standard fuels. So, that means for any fuel, if you would like to designate the octane number, if you would like to define or if you would like to identify the octane number, what we need to do is we need to test that particular fuel and we need to compare the self ignition characteristics of that test fuel to that of two standard fuels for which we already know the octane number. So, this octane number, the numerical value of a test fuel. So, octane number, this is a numerical value. So, the numerical value of a test fuel is obtained by comparing it to that of comparing it. I am again writing this. What is this it? Comparing the self ignition characteristics. So, this is the self ignition characteristics. Okay. So, the self ignition characteristics to that of two standard fuels. Again I am underlining these words, two standard fuels. What are those standard fuels? So, two standard fuels are isooctane so that means we can compare, rather we can predict the numerical or we can predict the octane number of any test fuel if we compare the self ignition characteristics of that fuel with the self ignition characteristics of any of two standard fuels, because we know the octane number of these two standard fuels. So, isooctane that is isooctane whose octane number is equal to 100 and another is N-heptane and whose octane number is 0. So, that means we are considering two extreme values of octane number. We are considering one fuel N-heptane whose octane number is 0 and you are also considering another octane number which another fuel whose octane number is 100, and if we compare any test fuel, rather if we go for testing of considering that particular fuel in a given or specific test engine and specific condition. So, basically say we would like to have the octane number of any fuel x. So, we can consider that fuel x, we can take that fuel for testing in a specified condition in a specific engine and we can compare with the octane number of that fuel with these two standard fuels and we can generate the numerical data. So, this is the octane number. So, similarly this is, so basically you can see that isooctane is having octane number 100 while the N-heptane is having octane number 0. So, let me write here. So, octane number simply octane and this is also known as ON. So, octane number 100 and octane number 0. So, what is the physical significance of this number? Higher the octane number, less likely the fuel will self ignite. So, that means if the fuel is having higher octane number, it is less likely that the fuel will self ignite. So, if I now ask a question, for the compression ignition engine or CI engines, the fuel will be having higher octane number or lower octane number or lesser octane number. So, the fuel which will be used for the CI engines must have higher octane number, because since the higher octane number, the fuel with higher octane number is having less tendency to self ignite, right, because you know for the compression ignition engine we are having higher compression ratio. So, the rise in temperature due to compression heating would be a rise in temperature of the air due to compression heating would be higher, and if you are using a particular fuel that at that temperature fuel will self ignite, then it will lead to knock that I have discussed already. So, that is why to prevent knocking, CI engines are preferred, I mean the fuel which is having higher octane number are preferred for the CI engines. So, higher octane number, let me write over here. So, I can write here that higher octane number fuel with higher octane number is used for which is very important for higher compression ratio engine, higher compression ratio engines. Since CI engines are having higher compression ratio, so naturally the fuels which will be used or those will be used for the CI engines must have higher octane number, because we can prevent the detonation. So, this is very important. That means, it simply indicates low compression ratios can use engines of low compression ratio can use low octane number fuel with lower octane number, right. So, this is very important. So, now if we go to the next part, that is what we have discussed today, that if we go back to the previous slide here. So, you know that we are supplying fuel into the combustion chamber and the compressed air temperature is such that the moment at which fuel is supplied, it will the combustion will initiate and combustion will be completed within the stipulated time. Now, question is, so for the selection of fuel, typically for CI engines, a knowledge about the ignition at precise time is very important. So, basically you know that we are compressing air and towards the end of the compression stroke, nozzle is fuel is supplied into the combustion chamber through the nozzle, and then entire fuel will mix with the air and combustion will be completed. So, what is most important for the CI engine is that if I write here that for the CI engines, which is very important, is that self ignition is a necessity. self ignition is a necessity. Now, that means it indicates that, so which is important, the fuel will be selected, right, such that it will self ignite at a proper time right. That means which indicates that knowledge and control of the ID or ignition delay is very important. Right. So, if we had seen that higher the rise in temperature above the self ignition temperature, shorter is the ignition delay, right. If shorter is the ignition delay, we can have very quick rise in, I mean very quick completion of the combustion, and this is desirable. So, for the CI engines in which self ignition is a necessity, we must have a knowledge and control over the ignition delay to ensure that combustion is completed smoothly and that too quickly. Now, we cannot even select any particular fuel for the CI engines unless we know that that is suitable. So, that means again, unlike the octane number, there is another number which is called as Cetane number, which is used to describe about the ignition delay about a particular fuel. So, the what I had written over here is that the knowledge and control of ignition delay is necessary, and this property, this is very important, the property that quantifies this particular aspect is the Cetane number. So, for any fuel we must know about the ignition delay. As I told you that ignition delay even for a given air fuel mixture is very ambiguous, it depends on so many things. So, the property that provides or that quantifies about the ignition delay of a fuel is the Cetane number. So, let me write over here again. So, Cetane number or Cn, that is, so is the number. So, basically this number quantifies the ID of a fuel, that is ignition delay of a fuel. So, this is not only the ignition delay, but also about the knowledge. So, this is the Cetane number. So, this Cetane number again if you would like to have for any particular fuel, this is again a numerical number, and if we need to go for the calculation of Cetane number of any particular fuel, we need to compare the ignition delay of that particular fuel with two standard fuels. So, again we need to take the test fuel for testing in a specific engine in a specified conditions, and we need to compare the ignition delay to that of two standard fuels, and then we can generate this numerical number. So, the Cetane number of any fuel is, what are the two standard fuels? So, two standard fuels are used to generate the numerical value of Cn of any test fuel. And what are those standard fuels? One is N-cetane, that is N-cetane plus the cetane number is, this cetane number is 100, and another one is heptamethyl nonane. So, this is having cetane number 15. So, it is having cetane number equal to 15. So, that means it is not 0. So, we should be taken this is N-cetane, that is having cetane number 100, and this is heptamethyl nonane which is having cetane number 15. So, it is not a fuel which is having cetane number equal to 0, right. So, this is multiplied with, so if I write here, plus 0.15, that is because of its cetane number. So, these are two standard fuels. Okay. So, we have talked about the kind of self ignition characteristics of a fuel, and also we have tried to understand why this particular property of the fuel is very important even for both the engines, CI and SI engines. And finally, we could define two important numbers, that is the octane number and cetane number, and these two numbers, the knowledge about or the numerical value of these two numbers are very important to know about the self ignition properties as well as the knowledge about the ignition delay, and the knowledge about the ignition delay as well as self ignition property is very important to select any particular type of fuel for any particular engine for its smooth operation as well as to prevent the undesirable phenomenon like knock. So, now finally, we shall discuss about the alternative fuels. Question is, we have talked about the gasoline in the last class, right. So, keeping in mind the possible scarcity together with the cost associated with the gasoline extraction, effort has been taken to explore several avenues of the alternative fuels. Though attempts have been taken to modify the design to bring the fuel economy, even then the dwindling supplies of the gasoline allows to figure out several alternative fuels. So, today we shall discuss about two alternative fuels which are also used not in a purely in a pure form, but in blended form with different proportion with gasolines. So, one is alcohol. So, here we will be having methanol, ethanol and another one is hydrogen, right. So, you know the methanol, ethanol, we have talked about normal paraffins. So, if we recall and if we replace one hydrogen atom with the hydroxyl group, so we will be getting alcohol. So, alcohols like methyl alcohol or ethyl alcohol, that is methanol and ethanol, as well as hydrogen, they are they are used as an alternative, as alternative fuels for the internal combustion engines. Now, question is, when you are talking about alcohols or hydrogen, certainly if we try to recall, in the last class we have talked about the limitations of gaseous fuel. One is the storage, and also there is a possibility of having leakage. So, if we now try to discuss about the advantages as well as disadvantages of alcohol as well as hydrogen. So, why not alcohol is purely used, is used in a pure form, or even though hydrogen is having promising potential to be used as an alternative fuel, but even then why it is not so used even with the advent of new technology. So, what I will be doing, I will be writing several advantages and disadvantages of alternative fuel. So, first we talk about these alcohols. So, alcohols, right. If we write the advantages first, number one is this is available in plenty, both naturally and manufactured form. Second is, it is having high octane number. We have talked that if a particular fuel is having high octane number, that means it has less tendency to self ignite, and this is good for the engines having higher compression ratios. That means, it has, even if we use that particular fuel for the engines having higher compression ratio, tendency of having knock is not there. High octane number, and then most importantly low emission, and low sulfur content, and finally, which is very important, is that when burned gives more moles of exhaust right. That is, it simply indicates more power output. So, when burned it gives more moles of exhaust, so pressure will be more, definitely power output will be more. So, all these are advantages if we use alcohol as an alternative fuel, but at the same time we cannot deny several disadvantages as well. What are those? So, if I write alcohols. What are those? Low energy content, if we compare a particular alcohol with the gasoline, then definitely the energy content of alcohol is less, almost half than that of the gasoline, and one serious disadvantage is that more aldehyde emission, right. It is because of this chemical structure of the alcohol, and it is also more corrosive than gasoline, on several materials like copper, aluminum, brass. So, it is having more corrosive nature than gasoline on several materials like copper, aluminum and brasses. So, these are the several disadvantages. So, now if we look at the hydrogen, the promising potential of hydrogen as a fuel. As an alternative fuel. So, we write again, first we can write the advantages. It is having again high octane number, so we have already discussed about the benefit of having high octane number of any particular fuel, then low emission, right, and finally fuel availability. We can again have natural sources, we also can get hydrogen through the electrolysis of water. So, the availability, emission as well as high octane number, all these are basically low emission, particularly NOx emission can be kept at a very low level. So, NOx can be kept at a very low level. So, this is very important advantage of hydrogen to be used as an alternative fuel. But at the same time we cannot deny several disadvantages. What are those? So, if I write over here only, this is in line with what we have discussed in the beginning of yesterday's class, that is storage issue, that is heavy and bulky storage, right, and fuel can detonate as well. Number 3 is low poor volumetric efficiency, right, poor volumetric efficiency, because to burn certain amount of hydrogen to get equal amount of power we need huge amount of air. So, this is in a way and this is in a way not. So, basically heavy and bulky storage fuel can detonate. Poor volumetric efficiency, that I already told, that it is if we use hydrogen, then to get certain amount of power, if we compare with gasoline, then we need to supply huge amount of oxygen. So, that simply indicates that it is having poor volumetric efficiency, and also it is difficult to refuel. Right. So, all these are the disadvantages. So, having several advantages, we also could write several disadvantages as well. So, though hydrogen is having promising potential, for an alternative, I mean as an alternative fuel, but we also can see today that still it is having several disadvantages. Attempts are taken, still research is going on for efficient use of hydrogen. Most important concern is the storage, so that gasoline can be replaced by this particular fuel and we can bring fuel economy. So, to summarize today's discussion, we have talked about the self ignition characteristics of the fuel, then we could define two important numbers, and the numerical value of these two numbers is very important to select a particular fuel for any particular type of engine. Finally, we could discuss about the alternative fuels which are typically used for the internal combustion engines. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.